We should start with the last lecture of today. So if the people in the back can just take their seats, we can start. So the last lecture of this morning session will be given by Sandoval from the Physics Institute at UNAM, and he's going to talk to us about the Hawk Observatory, looking at the most energetic light in the universe.
Yes, hello. It's a pleasure for me to present to you this new observatory that we have built in the high mountains in central Mexico. It's a kind of a rather sui generis observatory because it's looking at the universe with large water containers. I will tell you how we do that. So the plan of my talk, the outline is to give you some science motivation, how we do the detection of these very high energy photons, what are the galactic sources that produce them, what are the extragalactic sources, and what kind of fundamental physics we hope to learn from them. Tell you what is in the planning as a further evolution of this program, and finally I will go on some more archaeological discussion about why Hawk was built in Mexico. To start with, I will show you here what is the non-thermal universe that we observed. Most of it we know from cosmic rays. As you know, the spectra of cosmic rays spans more than 10 orders of magnitude in energy, going up to the 10 to the 20 electron volts, and comprises a part that is thought to be produced in our galaxy, and a part that is thought, a high energy part, that is thought to be produced outside of the galaxy. And we know that it's about the energy in our neighborhoods, about 1 electron volt per cubic centimeter in charged particles. And this is about the energy that we have in photon, electromagnetic fields, or cosmic microwave background. And as we see, nature is able to accelerate particles to 10 to the 20 electron volts. That's over 1 joule of energy in one single particle. And so what we want to know is what sources, astrophysical sources, are able to produce and accelerate these particles, how is this done, and what kind of new physics we can learn from that. And the question is, why don't we use the cosmic rays themselves to probe the universe? The reason is very simple. There are very high, relatively high magnetic fields in the galaxies inside the stellar environment, and this turn the charged particles so that we lose completely the directional information of where they are produced. So with charged particles up to now, we are not able to find the sources where they are produced. And so these charged particles can interact and produce neutrinos or gamma rays, and those, as we know, they are neutral and are able to propagate in straight lines through the universe, and therefore neutrino astronomy, gamma ray astronomy is the way to probe these sources that we think most of them are powered by black holes' extreme gravity situations. So we have neutrinos in the very high energies. These are very difficult to measure, but as you know, in the South Pole ice cube and in the Mediterranean, Antares are able to detect now neutrinos, very high energy neutrinos in this energy range. What I will concentrate more is in the GeV to TeV gamma rays and what they tell us about the universe. The problem that we have is that these gamma rays are not primary particles. They are really produced by charged particles in different situations. They are produced by electrons, by synchrotron emission, when the electrons spiral along the magnetic fields in the universe. They emit gamma rays. By inverse Compton scattering, where a high-energy electron upscatters a photon to very high energies. By synchrotron self-Compton, when you have both effects. And by hadrons, they are produced by very high-energy cosmic rays interacting with the medium and producing many particles, among them pi zeros, and these pi zeros immediately decay into photons. Or also exciting protons with a background light, producing also high-energy gamma rays. And there is the speculation that dark matter either can self-annihilate or decay into many particles, and eventually out of those decays we will see gamma rays. So there is a possibility that we might observe dark matter annihilation or decay from there indirectly in the gamma decay. The sources that we know that produce these very high energy gamma rays are in the galaxy, pulsar wind nebulas, that here is the Crab Nebula, that you see it's exciting all the environment, the gas around it, pulsars themselves, supernova remnants, and X-ray binaries in which we have a black hole surrounded by an aura binary star, a large star, which is creating matter and then emitting jets of particles and gamma rays. Extragalactic, we have AGNs, active galactic nuclei, where the supermassive black hole in the center of the galaxy is again creating mass and spitting huge jets of particles and gamma rays. We have starburst galaxies in which there is, due to the interaction with another galaxy, a huge star formation and supernova production. And then we have the gamma ray bursts, GRBs, that are known to be of the two types. One is a long gamma ray burst that lasts more than 1 second and shine more than the whole universe during that time due to hypernova explosions, or shorter ones, less than 1 second, in which we have two very compact massive objects like black holes or neutron stars that collide, creating a larger black hole and emitting these jets of particles. The problem that we have with detecting very high energy gamma rays is that the atmosphere is opaque to these particles. As you know, there are only small holes, one in the radio, in the infrared, in the visible, where the atmosphere lets the gamma rays, the photons, shine down to the Earth. And at very high energies, we have no chance to get them at the ground level. So a large program has been developed to measure gamma rays at the satellites, but this only can go to a certain energy. Up to above that, these detectors are of the order of 1 square meter. And so the fluxes of very high energy gamma rays in the TeV range are so small that you cannot detect them with 1 meter detector up in space. So we have to do a trick, and the trick is to use the atmosphere as part of the detector. So we have cosmic rays or gamma rays that interact in the upper part of the atmosphere, about 40, 50, 100 kilometers high up, and start developing a shower of particles, electron, positrons, low energy gamma rays, and these propagate at the light speed through the atmosphere, coming down to the ground. And there are two ways then to detect these showers. One of them is looking at the Cherenkov light that is emitted by these particles as they travel in the atmosphere. As you know, the Cherenkov light is produced by charged particles propagating faster than the light speed in this medium. We have air here, and therefore it has an index of refraction that is smaller, that is bigger than 1. and therefore these particles emit Cherenkov light, and they do it in a very small cone focusing along the direction of these particles. So having large parabolic detectors that collect this light into fast cameras, we can detect these showers as they come in the atmosphere. Another way is to detect at the ground all these particles themselves. And to do that, we have to be high up in the mountains to be able to collect a large fraction of these particles, because they start being attenuated at about 6,000 meters above sea level. Beyond that, they start decreasing the number of particles as they propagate. So this is the present status of very high energy gamma ray telescopes. They are this type of atmospheric Cherenkov telescopes. There are 3 in the world at the moment. One is called MAGIC in the Canary Islands, in La Isla de La Palma, where they have these 2 big detectors. There is another site in Arizona called Veritas that has 4 of these big detectors. And there is one more in the southern hemisphere in Namibia called HES that has 4 smaller detectors and one very large like this. There was in the past a detector, Argo, in the Tibet that had an array of charged particle detectors to detect the shower particles themselves at ground level. And just recently, we have inaugurated HAWK in the mountains of central Mexico. And finally, IceCube in the Antarctica is also able to measure high energy particles, muons, and gamma rays. The advantage of a satellite detector, space-based detector, like at the moment the Fermi detector, Agile or Egret, is that they have a wide field of view. They convert the gamma ray into a pair of electron positrons, and these are detected by a normal high-energy physics detector, and therefore they are about 1 square meter of area of what they can detect. They are continuously operated. They have a very wide field of view. They have low backgrounds, but the small area limits really what is the highest energy that they can detect, and they have moderate angular energy resolution. The air Cherenkov detectors, like Veritas, HES, MAGIC, and before Whipple, that was really the pioneer in this field in Arizona and Hegra in La Palma, have the best angular resolution. They are pointing very precisely at one spot and then seeing what are the gamma rays that are producing there. They have covered large area, have low background, but they have to be pointing exactly at the source they want to look at. They cannot cover a large field of view. And they have low duty cycle because they can only observe at night, very dark nights when there is no moon, to see this Cherenkov light from the particles propagating in the atmosphere. And finally, these extensive air showers, they are detecting the charged particles with detectors on the ground. They have a wide field of view. They are continuously operating, have a large area to detect high energies, but they have moderate angular and energy resolution and moderate background rejection to detect what is a gamma and what is a cosmic ray. Here I give you, as function of energy of the gamma ray, what is the sensitivity for different detectors. Here is the satellite Fermi, what it can detect. This is energy, E squared dNdE, and this is the spectrum of one of the brightest sources that we have around us. That is the supernova remnant from the crab that exploded in the year 1045, reported by the Chinese head astronomer, telling the emperor that there was a guest star that just appeared and was visible even during the day. So this crab nebula has this spectrum, and then Fermi can detect this range of energies and this is sensitivity. The air Cherenkov telescopes are about here, and our new detector can be here, HAWK 300, in 1 year or in 5 years of data taking. the air Cherenkov detectors, just to show you how they work. Here is the cone of Cherenkov light produced by the shower as it propagates in the atmosphere. And then 4 detectors or 3 detectors will detect these showers, and then they can determine the axis of propagation of the shower in the atmosphere, and then triangulate to see exactly where it's coming from. And that's what gives them this very superior resolution, angular resolution. This I skip. The Hawk detector is the extensive air shower detector that collects the charged particles from the showers as it propagates in the atmosphere. Is sited at 4,100 meters near the highest mountain in Mexico. This is the Pico de Orizaba stratovolcano. And we are in the Sierra Negra volcano, an old extinct volcano. This is an active volcano, actually. Last time it exploded is a little bit after the Spaniards arrived in 1450. It consists of 300 water Cherenkov detectors that are 7.3 meters in diameter and 4.5 meters deep, containing about 200,000 liters of very pure water. And they cover an area of about 20,000 square meters. The way they work is the air particles from the air showers, they enter the water, and at that moment they produce Cherenkov light, and this is observed by 4 high quantum efficiency photomultipliers sitting at the bottom and looking at all the volume above them. And then we detect about between 20 and 40,000 signals per second in any of these tanks, any of these detectors. So we have a huge amount of showers arriving at this detector, and we collect only about 20,000 per second that are big enough to be interesting for us to analyze them further. The detectors are made out of a corrugated steel bolted together to be able to produce these tanks at this very high altitude. Once they are built, we have to put in a plastic bag, we call it a bladder, and fill it with water that is purified on the site. And here are the detectors, large area photomultipliers to look at the light produced by the Cherenkov emission of the particles traversing it. So here is the detector. It's an event that before it was completely finished constructing. It has now 300 of these tanks. And what I show you here is the signals that arrive at the different 4 photomultipliers in the detector. And the color coding is the amount of light that they produce. So you see there is a center where there is a lot of light being produced, logarithmic, about 10,000 photons we produce here, while at the edges we are at about 1 single photoelectron that is produced. And so out of this we then determine the center of the cascade and determine the angle from which it comes. And the way to measure the angle is by looking at the time dependence. Here we see in fractions of nanoseconds how the signals propagate through the detector. And out of this, we fit then the shower plane, and the perpendicular to the shower plane tells us where is the source that emitted this photon. Yeah? So with big water detectors, we can look precisely at the very high energy gamma ray sources in the universe. The site, as I told you, is near central Mexico, about 200 kilometers from Mexico City in Puebla. Here is the Pico de Orizaba, the highest volcano in Mexico. This is the volcano Sierra Negra. Up at the top of the Sierra Negra, there is a radio telescope, large millimetric telescope, and on the flanks, it's where we have built the Hawk detector. It's at 90° north. So here is where how we reconstruct the data. The particles come in, produce Cherenkov light. We measure the time of arrival. And here are all the tanks squashed in these blue circles. and the vertical lines is the time of arrival of the signals. So you see that they fit well a shower plane, and then the perpendicular to it is the direction from which the shower came. The observatory, you see here an image from the day we made the inauguration, the 20th of March of last year. This is the volcano Sierra Negra. So it's been built modularly. And so we started in the beginning of 2013 with 30 of these tanks. We put them in operation and started taking data. Towards August of 2013, we had 111 tanks. And then we took about 1 year of data while we constructed the rest of the detector. In November 2014, we switched to Hawk 250, that is this area here. And finally, beginning of last year, we started with the full detector. Yeah, the inauguration was the 20th of March. And by now, we have 1 year of data taken with the full detector that we are just finishing, analyzing, reconstructing. So here is a preliminary map of what Hawk sees in high-energy gamma rays. This is plotted in the galactic coordinates. So you see here in this plane is the galactic plane. This is the inner galaxy. The center of the galaxy is around here, so we see many sources on the inner arm. And then on the outer arm, we see mostly the Crab Nebula, and then Geminga and other sources. And we see also some blazars, Markarian 421, Markarian 451. So this is a preliminary old plot from when we had 150 days of 250. We are just finishing analyzing the new data. So here is the Crab Nebula. Then there is the galactic plane, the Markarians, two blazars that we see, and the Geminga, very nearby, very interesting pulsar remnant that I will talk about in a moment. So by now, this is the data that I showed you. We have been learning how to calibrate, how to optimize our reconstruction of the events. And this is the Crab resolution that we had at that time. Now with the new version of the reconstruction software, we have focused the detector. It has a much better resolution and sensitivity. So we hope we will see very nice things. Here is two plots of the performance of the detector. Here is the number of photons on the Crab as a function of the distance from the Crab position. So you see, we see the Crab with a very high signal to background ratio and within 0.1 degree square of resolution. And here is another plot that shows the discrimination between charged particles, charged cosmic rays that are about 1,000 times more frequent than gamma rays, and this is our gamma ray signal, just a small fraction, 0.1% of all the showers that we reconstruct. So about the galactic gamma ray sources, as I told you, we see nebulas produced by the pulsar wind as they interact with the environment. And one interesting thing about them is that, as you know, recently there was a detection on the excess of positrons from AMS and Pamela. And the question is if they are produced by dark matter or by a close by supernova remnant. Yeah. We also measure X-ray binaries. We are looking to detect more of them because they have been not all explored all the size for it. And the pulsars also tell us very interesting things about fundamental physics. So here is all the data from Hawk 111 of the galactic centers. At the moment, I told you we are analyzing the new data. Looks very much more precise, but we fit them with about 11 sources that are most of them known. We have found some unknown sources that maybe are pulsar binaries. Here is the spectrum of positrons, excess over electrons and positrons that has been measured by Pamela and then confirmed by Fermi and AMS. And you see that as function of the energy, there is suddenly an increase of positrons over the total number of electrons and positrons. And this is a very interesting signal that has been, are milliards of explanations for it at the moment. But if we have a nearby old remnant of a supernova that is close enough so that the electrons and positrons reach us directly, this could be the source of this excess of positrons. And we are analyzing now the source of this Geminga pulsar and another pulsar that is nearby, supernova remnant that's nearby, to see if they are the source of these electrons and positrons. Also, here's a spectrum of different supernovas measured by the Veritas Ercherenkov detector. And what we will do is then extend this spectra to very high energies and see if the sources are leptonic, created by electron acceleration or by cosmic ray acceleration, and find the sources of it. Also, recently there was a discovery of new X-ray binary, another small stellar-sized black hole with a star around it. That was the correlation between X-rays detected by SWIFT and gamma rays detected by Veritas. We, since we are looking at all the sky all the time, are in a good position to look for unknown sources as they flare up. And also here is a spectrum of the crab, and it's much harder than it was ever thought a pulsar should be. And so we will continue making these measurements at very high energy. We go up to hundreds of tera-electron volts. In extragalactic sources, we have active galactic nuclei. And the question is if the blazars that are the active galactic nuclei, IGN, that have the jet that they emit pointing at us, if they are the ones that accelerate the highest energy cosmic rays. We have starboard galaxies that produce a burst of new stars that also create a burst of supernova remnants. And it's also the source of the gamma rays, high energy gamma rays that arrives to us. And then there are these gamma ray bursts, and we are looking to see how we can detect such phenomena. Here is a picture of Hawk 111, still more or less sub-threshold, looking at Markarian 101, and there you saw it suddenly flashes. This is day by day what is the signal that we get by it. And so we can produce light curves of all the sources that are above us during the hours that they transit every day above us. And in comparison to these Markarian light curves, you have here the light curve of the Crab Nebula that is very steady, although the last few weeks it also started flaring up. And this is something that is known, that the Crab is not completely flat, but it has some incidents of flaring. The Crab Nebula itself, here is the Markarian 421, this interesting blazar. And this is the coverage up to now by different detectors on different wavelengths. And you see it's very sparse. There are just times where they have time to look at it, and suddenly it doesn't flare, and suddenly it flares, and then many other detectors look at it. What we will do is we will look at it for over 10 years continuously to see how it behaves. Not only this, but the other blazars that we are able to see. Here is another instance of a very a giant flare from a blazar, B21215, and here is the data from the Fermi satellite at low energy gamma rays, and here is the point measured by Veritas. And so this is the thing that we will be looking at. Also interesting is to see the pulsars themselves. As you know, the pulsar is a neutron star, very rapidly rotating. The Crab Nebula turns around itself in 33 milliseconds, 30 times per second. And this is the data at 50 to 100 GeV. And it was not thought that these pulsars are able to produce such high energies. And what we will be doing is extending this measurement from 100 GeV to several TeVs and see if the pulsars themselves are still emitting at these very high energies. This is a physics that goes about it. You have extremely high magnetic fields and at an angle to the rotation angle of the neutron star, and that's what then shines us like a light that suddenly shines into our direction, and we see the pulsing. There are other instances of blazars, a black hole that is suddenly, in matters of a few minutes, can shoot up several orders of magnitude. And this is very interesting to see how it is possible that you have such small distances being able to accelerate to such high energies particles in this vicinity of the very huge black holes. There is also a very interesting measurement done in which we have AGN with a gravitational lens of an intermediate galaxy between it. And this turns out to be at a set of 0.939. And actually, it was thought that the gamma rays at these energies would never arrive to the Earth because they interact with the background light in the galaxies. Here is what we see. The measurement was done first by Fermi in low energy gamma rays, and then MAGIC looked at it. And then a few days later, it was able to detect the second pulse coming from the upper lens that was delayed by about 10 days to the directed one that Fermi detected. So as I told you, the absorption into the external background light, it's thought to make the gamma rays absorbed into produced electrons and positrons, and propagating to a set of about 1 is maybe only possible if you have intermediate axon-like particles that propagate and permit very high energy gamma rays to reach us. Finally, on gamma ray bursts, we expect 1 or 2 per year to have enough energy in our field of view to be able to detect them in the TeV energy range. Just yesterday, there was one above us. There are about 1 every week, more or less, that flares just above us. We still haven't learned how to detect them, but if they emit gamma rays into the TeV energy range, we would be able eventually to detect them. So this is an ongoing project. And finally, to explore what can be done with these very high energy gamma rays, probing fundamental physics. In terms of cosmology, probably one can measure what is the attenuation of gamma rays by the infrared photons on the external extragalactic background light. And so maybe they can tell us something about the evolution of the universe. We can probe the Lorentz invariance if the photons of different energies travel at different speeds through the universe. We can look for dark matter and see if somewhere in the universe there are regions of dark matter annihilating or decaying and producing gamma rays. And since we are a very large field of view detector, we will be able to sample many sources. So here is a cosmological infrared extragalactic background light. Essentially what this happens is that the very high energy gamma ray in the TeV range interacts with a photon in the EV energy range and produce an electron positron. And here you have a plot as function of the set of the source and as function of the energy of the gamma ray of what is the optical depth that we can look at. And about the set of 0,3, we can look at the tens and hundreds of TeV gamma rays, but at the set of 4, we can only see gamma rays of a few tenths of a fraction of 100 GeV to propagate through the universe. So this is about the range that we expect from gamma rays. But as you saw, this lensed laser that was seen, it was measuring at set equals 1 at energies of the order of several tenths of TeV. So we will see what we can do. Also, Veritas just very recently was able to look at the flare from this laser, PKS 1441, and the convoluting what you observed from what is the models of electromagnetic background light. You can then limit what is the spectrum here in the micrometer wavelength of the background light. So this is the type of measurements that we hope to be doing continuously. Also regarding the Lorentz invariant violation, if you have sources that produce gamma rays instantaneously of different energies, we can look them how is the time of arrival between low energy gamma ray detectors like Fermi and high energy gamma ray detectors. Here it's done in the Crab pulsar, checking exactly the correlation between the arrival of the pulsar light in the Fermi at 100 of GeV with the arrival of 100 MeV in Fermi and about 100 GeV in Veritas, and we will extend that into the TeV range and try to constrain then the Lorentz invariance violation. Regarding dark matter, you have here discussed a lot what are the places where there is a large enhancement of dark matter in the galactic center, dwarf spheroidal galaxies, galaxy clusters, or maybe identify sources. And we will be looking at all of them and see if they produce anomalous gamma rays that can tell us something. And this is the type of sensitivity that we have of dark matter. Here is just one channel, dark matter annihilating into W's and then producing gamma rays. And this is the limit that we can set on the product of the cross-section and the velocity of the gamma rays as function of the invariant mass of the dark matter. If we are very high up in the TeV range of dark matter masses. So what next? There will be upcoming a new atmospheric telescope detectors that's called CTA. It's a huge astronomical facility that will construct one in the north and one in the south. And regarding the air shower detectors, I will show you that in HOC we are already doing an upgrade, and we are also discussing the possibility to build such a detector in the southern hemisphere to look at the sky continuously. So the CTA is an array of different size Cherenkov telescopes at two sites, one in the north, probably in Canary Islands, one in the south in Chile, that will cover both the hemispheres with very good resolution. In HAWC, what we will do is we will extend the area of our detector by a factor of 4 by putting small water Cherenkov detectors, about 1/100th of the volume of our normal HAWC 300 detectors. And this is to be able to detect the center of the showers, very high energy showers that fall outside of the detector and still illuminate our array with enough particles and deposited energy that we can reconstruct the showers very well. But we had an ambiguity between the distance of the core and the angle from where it comes, and that spoils the angular resolution. So by putting these 300 detectors out here, covering a factor of 4, we will increase the factor of about 3 to 4 the efficiency to detect very high energy gamma rays. And as I told you, we had an idea to start lobbying for making such a detector in the southern hemisphere. The ideal place is in the Andes in South America, a site like Alma in Chile, or in Argentina, or in Bolivia. There are many sites close to 5,000 meters. The higher, the better for these detectors. And we will see in the next few years if such a project can be started. And to finish, let me tell you some kind of a surprise that we got once we finished HAWC. Because as you know, the ancient civilizations in Mexico and Central America were very good astronomers. They had observatories in many places of Central America, and they were able to develop very accurate calendars. They were able to predict eclipses, the transit of Venus, etc. And what probably you don't know is that they also had very high altitude observatories that are called Tetzacualcos, that are small structures that are high up in the mountains at 3,000, 4,000, 5,000 meters, that aligned especially to some directions, astronomical directions of the rising or setting of sun, moon, planets. And these Tetzacualcos, they are all over in the high mountains of Mexico. But there is one that is very, very special, something that most of us Mexicans don't even know. And we came into that because just recently it was the 50th anniversary that this stone was taken for the place where it was resting for 1,000 years to the National Museum of Anthropology in Mexico City. The then president, López Mateos, told their people, now that we are finishing this museum, I need an emblematic statue at the entrance of this museum. And he sent them all over Mexico to look for monoliths or interesting sites. And they couldn't find anything that he was satisfied of. And then finally he remembered that as a youth in the Mexico Valley, in what's called Texcoco, he used to go hiking with friends, and there was a monolith sitting in the river, in the base of a mountain, and he sent them to look at this. This is this monolith, and he told them to negotiate with the town that is nearby, Coatlinchan. It was their god, and to negotiate that they take them to Mexico City. And he told them, the archaeologists told him that this was the statue of the rain god, Tlaloc. And so he negotiated with the elders of this town to take the sculpture of Tlaloc to this museum. And they laughed at him and they said, it's not possible. And he insisted, this envoy of the president, until they finally said, okay, if you can find it, go up to 4,100 meters and look for it. And they didn't understand what these elders were saying. And the next day, they started digging this out, to the consternation of the people of this town. And then finally, they brought a huge truck to carry it to Mexico City. The town was in fire. And that night, they went and cut all the chains and all the support of this monolith and threw it out of the truck where they had already put it. And so the next day, they sent the army, and that was the end of the negotiations. And what turns out is that this, what we think is the Tlaloc monument, here it's in the Museum of Anthropology. It's not Tlaloc, it's his sister. And his sister is here. Here is the rain god Tlaloc and his sister, and both are in mountains, and the water is flowing down the mountain. And here you have an astronomer sitting in the water and looking at the universe. Yeah. And this sculpture, what you see, it has small holes in it that had collected very special water. This statue was like this observer lying face up in the river, looking at the universe. And this was really collecting Cherenkov light from the universe. So why is this place, Coatlinchan, where this statue was found, so important? And it's so important because nearby there is the most important and highest altitude observatory in all Mesoamerica. This is in the mountain of Tlaloc, and this is the sanctuary. It's a huge sanctuary, has about 200 meters length, and existed from about the year 100 or 200, made by the Toltecs, way before the Aztecs arrived to Mexico City. And it was a place of peregrination for these central civilizations for many, many years. Here you see another picture of it, high up in the mountains. This is looking to Puebla. Mexico Valley is on this side. And why is this so important at that place? And it's so important because at this place, this is the mountain of Tlaloc, it's aligned with several volcanoes in central Mexico. It's aligned with the volcano of the Malintzin in the valley of Puebla. The Puebla city is right here. It's aligned with the Citlaltépetl, this highest volcano in Mexico City. And it's aligned with another mountain that's called the Tepeyac, that was sacred for the people from Teotihuacan. And so here is the Iztaccíhuatl, here is the Popocatépetl, two other major volcanoes in Mexico. And this is a place where the sun also is aligned with them. On the 12th of February, it rises just behind the Pico de Orizaba, and you see the Malinche in front, and you are at the Tlaloc mountain, and you see the shade of this mountain in the Tepeyac mountain. So it's this is actually the beginning of the Toltec calendar at that time. And so for more than 1,200 years, this was a place of peregrination for the rain god Tlaloc. But after the conquest by the Spaniards in 1539, it was ordered to be destroyed by Fray Juan de Zumárraga. Here you see the sun rising in the mountains behind it. But this was not all lost. The memory was kept alive by people on the villages all around this mountain. Here are what's called the graniceros, people that go up to the mountain to ask for rain to the Tlaloc god. And so this happens every year when they go to the peregrination. Very soon it will happen. And recently, with HOC, we built a second high-altitude observatory. And what turns out that, to our surprise, is that this line, that is the line following the avenue of the observatory of Tlaloc, is completely aligned with the line that we have in HOC in our mountain. So we were predestined to make HOC up there. So just to finish, Ms. Hawk has brought to Mexico one of the forefronts of astrophysics by observing with water detector the most violent fires of the universe. Thank you.
Thank you, Andres. Do we have any questions over there?
Sorry? The energy of the gamma ray is done by the size of the shower and by the amount of energy of light that deposit in the water Cherenkov detectors. Yeah. Yeah, even if the shower extends beyond our detector, we can fit the shape of the detected signals inside our array, and that is proportional to the energy of the primary gamma ray. Yeah. So there are lots of algorithms that we are optimizing, and we are trying to see what is the best that we can do. But this is how it's done.
Some other question? No more questions. Then we thank our speaker again.
Okay.
And I have just one announcement. The organizers have asked me to ask the people who own the posters to take the posters